Yaskawa.
Good morning, my name is Daniel Schubert and I work in the training department here at Yaskawa. I'm a product training engineer. This is the second webinar to a two-part series. Earlier this month we had the motor basics class where we talked about induction motors. We covered the components in an induction motor, the theory behind them. Then we covered the NEMA design types and nameplate information. The second part is going to cover variable frequency drives. For this webinar, we are also offering CEU credits. Since this class is going to run around an hour, you will receive 0.1 CEU credits for this course. To get that, you need to complete a short 5-question quiz and pass that to receive those CEUs. You can just go to training@yaskawa.com or email me directly and I can give you the quiz after this webinar and you can turn that back into me. Topics included today are as follows. Why would someone consider the use of a VFD for their application? Possible areas that a drive or VFD can be used in. Then we'll break down the various levels of a drive and explain those components and their use. Finally, we'll cover control methods and special design types. So special designs other than your normal drive layout, we'll discuss those, and also options that are available for drives. So with the drive, we can now control the speed of our motor and in some cases even the torque, depending on our control method. We have soft start capabilities, and this is going to help us to not have excessive inrush compared to starting across the line. This will also lead to a less harsh jarring environment on the rest of our supporting equipment. Built-in motor protection, so you can protect your investment. And also we have the possibility of energy savings with a lower speed available and or variable torque application. So possible energy savings. There's even the ability to have a zero speed servo-like characteristics for an induction motor. And also the ability to run high speed, so above your base frequency, as long as your motor can handle that. We also have the ability to do remote monitoring and control through communications. So you can monitor your system at your desk. If you guys joined us for the last webinar, you're going to notice that this picture seems familiar. This is our speed torque curves. Okay. So we didn't go into this in the last section just because I didn't want to blow it for the drives basics. So with a drive, we now have the ability to control and move our speed torque curve. So we can manipulate it and take advantage of our motor's characteristics at multiple speeds in this speed torque curve instead of at our across the line speed of 60 Hertz. So you would be running at full load torque in this area over here. Now we have the ability to change where this curve's located and depending on what speed you want to run, we can move this curve and give you full load torque down to a pretty low speed depending on your control method. This lower range can be anywhere from half a hertz all the way up to 1.5 hertz. So with this ability to manipulate the speed torque curve, we're able to take or use our motor in other situations than we normally wouldn't be able to use it for. So let's talk about some applications. One of the best markets for a drive from an energy standpoint would be a commercial application. The commercial market is full of these fans, pumps, and cooling towers. Even fan arrays are becoming big. And this application is a variable torque application, which will allow us to use the affinity laws, see some huge savings with the use of our VFD running at a lower speed, if possible, for our application. Most of these applications require one of our simplest control methods, so very easy to set up. And then we move to our industrial applications. In the industrial world, we may need very precise control. So at this point, we may need some kind of feedback or tighter control than what we would have with just a basic fan or pump. Not saying that industrial applications do not have fans or pumps, just a lot of them, a lot of other applications require this precise control. So we could have conveyors, presses, fans, pumps, winders, high-speed machining. That's just a few applications that can be seen in the industrial world. Looks like we have a question that popped up. See if I can answer that before we move on. With the VFD, you can give high torque at low speed. Yes, we have the ability to give you high torque at the low speed. Depending on your control method, this can change. And we'll talk a little more about this a little later whenever we get into control methods. So how much torque that could be available at these low speeds. All right, let's start to walk these drives. To start out, we have these different enclosure types. So depending on the environment that these drives can be subjected to, the enclosures vary quite a bit. Anything from an open chassis, a NEMA 1, NEMA 3R, NEMA 4, 4X, and even 12. Just to name some of the enclosures that are available. Their uses could be anywhere from indoor use with a light degree of protection. So maybe there's just a little bit of dust, but a fairly clean room that this drive's located in, all the way to maybe it's for outdoor use on top of a rooftop in the middle of summer in Texas or a winter in Chicago. So just varying degrees of enclosures, so they change a little bit depending on what kind of environment you're going to locate them in. And some of these even have hose down capabilities, so you can spray them down with a hose like the NEMA 4X. All right, let's talk about the different drive levels. We have our control, power, and main circuit. So our control is where we actually are getting our command, our brains located at. Then we have our power circuit. That's kind of the talking in between the main circuit and the control logic, and relaying the necessary information for, let's say, feedback or just maybe we want to monitor DC bus voltage, or we want to see what our output current looks like. So our current waveform. And then we have our main circuit, which is our higher voltage part of our system, where we're going to be moving all of this power and converting it to something that's more usable for our motor. So instead of our motor being stuck at running at 60 hertz, this motor is now going to have the capability of running, depending on the motor type, varying speeds up to that 60 hertz or even higher than that. So that's with the main circuit. Let's start out by talking about control. So our control's broken up into a couple different things. Our input, most of the time, probably comes from our digital operator. So this is where you can input parameters, set up overloads, any kind of motor protection. Maybe you want to set anything as basic as X-cell and D-cell times for your motor. So you want it to, your motor to X-cell to 60 hertz in 10 seconds or D-cell in 10 seconds. Those can all be set with this operator or keypad. And you also have the ability to run from your keypad if you would want to, or run from, which we'll talk about in a second, maybe our terminal board and receive a 4 to 20 signal or 0 to 10 signal for our frequency reference. So telling us what speed we would like to run at. Some options could be available with our drive. This one just happens to have a encoder card located on it. So this drive could possibly have a encoder feedback. So it would be running one of our tighter control methods. So the performance should be very good out of this motor that we're connecting to. Then we have our terminal board full of our inputs and our outputs, all of our digital, so our ones and our zeros, and our analog signals, so our 0 to 10 or 4 to 20 signals are all located on our terminal board down here. This terminal board is nice. It's has non-volatile RAM, so if something was ever to happen to the rest of your drive but your terminal board was okay, you could just use your old terminal board in your new drive, as long as certain things are kept the same, like it's the same size and control method and software revision. Then we have our control board. So this is the brain of our drive. This tells the rest of my drive circuit when to fire the IGBTs, which we'll talk about a little later, or protect my motor, so observe current, or even protect my drive too. So this is where all those calculations are done. Now let's move to the power section. So this is the connection between the control board with all of our logic, and goes to our power board or gate drive board, which is located right above the operator in this picture. For this webinar, I just chose this is a A1000. I believe it's a 139 amp drive, so a medium sized drive for these pictures. So your power board or gate drive board is going to output the signal to fire your IGBTs. It's going to read back signals from your main circuit, like your DC bus level and your DC-CT readings. So your current readings that you're checking all the time, those all come through this power board, which convert it to something usable for the control board to look at. So it's the connection between that low power control board and the high power main circuit. And that's done through this transformer. It's just going to switch that high voltage to something usable to power that control board. These vary depending on the drive size. Some of our micro drives actually have all of these boards and the main circuit soldered, sandwiched together. So some of those smaller drives are going to be, if you're trying to repair them yourself, are going to be not as useful to repair, but luckily they're pretty cheap, so you might as well just toss it and grab a new one anyways. But anything I think over 25 horsepower on our A1000s, not a micro drive, would probably use a board similar to this. From our control to our power, our gate drive board, now we're on to our main circuit where all the magic's happening. So our drives nowadays are going from AC to DC and then back to an AC waveform. This output, or this AC waveform, I would not call it a sinusoidal waveform. It's more of a simulated AC waveform, and you guys will notice this later. So for our input side, you notice up in the top corner we just have our picture. We're talking about just the input, so the converter side. This is made up of some small capacitors, and these units right here, these are MOVs. Okay, so these are going to try to get rid of any excessive voltage transients that could come in, let's say like a lightning strike or something like that. It's going to try to protect this more expensive part right here. So these input diodes that we have coming in here. This is a diode out of that larger drive that I showed before, that A1000 139 amp drive. Right here is our incoming AC. That's where it would come in from this side. And then it's going to output our positive and negative portions that we output from our diodes. So a diode is kind of like a one-way train. So it's going to allow this waveform to pass on one side, but not on the other side. Okay, so it's going to kind of chop this AC in half and convert it to something that looks like DC, which it will evolve from this as we move to the next section of this drive. So we have our three-phase incoming 120-degree electrically isolated phases coming through here that get chopped in half, so this lower portion would be missing until we come over to our other side of our diode, which this diode right here has the upper and lower portion all in one module. So some of the smaller drives actually have all of these in one module and even have the output on the same module. So those micro drives, this is all actually one piece here, and then the capacitors will be probably soldered onto another board on those smaller drives. So that's our input or converter side of our drive. Then we move to our DC bus. Okay, so we've got the top part of that waveform that we chopped in half with our diodes. And since we have this capacitor here, we're actually going to start to fill in these voids, so it's going to smooth out this DC bus ripple, which is very bad for a drive. So things that would cause excessive DC bus ripple would be like if you would try to single phase a drive. You can do it, you just have to deal with a big D rate, so that would cause excessive DC bus ripple. But if we have three-phase incoming, you have that 120 degrees evenly distributed waveform going across here for all three phases, so it smooths out that DC bus quite a bit with the help of this capacitor. Also, whenever you first start up a drive, you're going to notice that it probably makes some clicking noises. This is because we're running through a soft charge circuit. So the soft charge circuit's made up of a contactor or set of contacts. This is just spreads out the load a little bit here for this larger contactor. And then we have a resistor. So we would not want to just hit this DC bus capacitors whenever they're not charged with our diodes chopped in half waveform, because that would just act like a short and would be very bad. So we have to slowly charge up these DC bus capacitors, and we do this with this soft charge circuit. When we first start up, we'll run through this resistor and slowly charge up these capacitors. Once we reach a certain level, the power board that we talked about before will read this and change, and then the contactor is going to close, and we're going to get our full power running through to these capacitors and finish charging them, and then we have all of our power available that's from our incoming three-phase power. I didn't mention it, and I don't have a picture, but some of these drives do have DC bus reactors. These are good for reducing some of our input harmonics, probably around 3 to 5% reduction in input harmonics. So you guys have probably heard a lot of stuff about input harmonics. Some drives have these. Sometimes they're optional, and you can add your own if you would like. Then we move to the last section where all the magic happens. So our output section of our drive, or our inverter, this is where our IGBTs are located, our insulated gate bipolar transistors. Okay, these have DC CTs. So instead of using CTs, we use DC CTs because our insulated gate bipolar transistor actually puts out a waveform that looks like this. This would actually be at a voltage output waveform. Our current waveform is going to look a little smoother, but we actually use DC CTs instead of CTs on drives. We also have this section here. Those are snubber capacitors for our IGBTs. IGBTs are similar to like MOSFETs, except a MOSFET's really for low voltage, really high switching frequencies. IGBT is for higher voltages and a little bit lower, or quite a bit lower switching frequencies. Still fast, not anything like the old days, but they're getting faster and faster too. So look for newer drives being able to run higher switching frequencies. These IGBTs have a gate that opens and closes. I like to think of this like a light switch. So you flip on and off your light in your house. That's how I like to think of this gate. So turning on and off this this power. But this happens very quick, okay? We'll talk about how quick and what that looks like in just a second, but just know that these are switching very fast, anywhere from 2 kilohertz to upwards of 15 kilohertz. Okay, so that's the gate. And then we have a emitter and a collector. Okay, and also this portion here. This is our freewheeling diode. So this allows our drive to take in regen. Okay, so whenever we decelerate a motor, we're actually running through these diodes and we're filling back up our capacitors. Once we fill up our capacitors, though, they have a certain limit. The problem with this drive is you can't go past this front end. So once that comes in through the diodes, it can't backtrack back out into our incoming line. So we're kind of stuck to fill up these capacitors. That's why people can trip out on things like overvoltage. So we have a very high DC bus voltage. And I don't think I mentioned it before, but you can always do a quick calculation to figure out what kind of DC bus voltage you have by whatever your incoming voltage is, times it by the square root 2, and then that will be your DC bus voltage. Okay, so we have these freewheeling diodes that allow us to regen back into these capacitors during like a decel. If there's different ways to mitigate that issue. You can use resistors to burn off excess energy. You can use one of our RC5s, DC5s to regen back on the line that way. You could add excess capacitors, or if you have another drive, you could do common busing between the drives. There's a bunch of different possibilities to try to get out of that overvoltage scenario, or just increase your decel time. That's the simplest way. So each of these sets of IGBTs are going to output a waveform. Okay, so we're building that sinusoidal or simulated sinusoidal waveform. Okay, so we have a positive and negative portion for each of these. So each of these are going to have their own waveform. So we are outputting three-phase simulated AC to our motor. Since we're doing that, we now have the ability to control what our frequency is and what our average voltage is. So let's talk a little bit about IGBT switching. So when do these fire and things like that? Remember, these are firing very fast. So T1, T2 shown up here is going to be for this first set. Let me get my mouse over there. So these two. And then whenever we move to the second set, we have our second waveform, and then so on, our third waveform. Now, we're going to work our way through this waveform, and at the beginning, let's just focus on this first output voltage waveform. Okay, so just focus on T1, T2, and what you're going to be looking at are these two. Hopefully, we'll see just our positive portion of our waveform blinking. So whenever it blinks, that means that's switching. So that switching's happening very fast. So we're just trying to simulate that so you can see this switching pattern. So focus on T1, T2, and there we go. There. So you notice how on these first two, which is for this waveform, this upper waveform, that just this top one was firing, okay? This bottom one will start firing, but we haven't reached that point yet. So if we go down to T2, T3, you're going to focus on these two. This is the upper portion of that waveform. This is the lower portion. So this one should come on just for a second, and then this other one should start switching after that. So let's see if that happens. and that happens. Okay, and then our last waveform here, we have our two IGBTs here, and we're going to start. Looks like we're starting on the negative portion, so this lower one will start up and then come over to our upper portion. So let's see if that happens. And there it goes. Okay. And the same thing's going to be happening as we move further through this. So you notice that for these, now it's just the bottom IGBT firing, and then through here, hitting the wrong button. For the second one, so these two, you're going to notice that it's the negative portion, and then the upper one will start to fire. And then so on for the third phase. So I think that shows pretty good how that switching happens. If you notice that these two never fire at the same time. If those two fire at the same time, that's not going to be good for your system. So there's usually this little bit of off time where we make sure that both of those don't fire. Let's talk about pulse width modulation. A lot of you guys have probably heard about pulse width modulation. We're going to follow from this. This is an actual output voltage waveform. We're going to use this and just use a simplified one. So with pulse width modulation, we vary the width of this pulse. This pulse is always going to have our full DC bus available. So this goes up to our full DC bus and actually can get even larger with long lead lengths due to voltage transients. So you're going to see full DC bus at the top of this. But with the IGBT, we're able to vary how long we stay on. So if we're trying to form this sinusoidal output, we're not going to stay on very long at the beginning. So for this full cycle that's available, or this full period that's available for this IGBT to stay on, we're only staying on a very small amount of time. Then as we start to build our sinusoidal waveform, we start to stay on more and more, okay? Until towards the middle, we kind of saturate and we stay on the whole time, and then same thing happens with the other side. We start staying on less and less until we reach that 0 point, and then the other set of IGBTs start firing. Okay? You can't really talk about pulse width modulation and not talk about carrier frequency. We talked about it before. IGBTs have a carrier frequency of usually they can be less than 2 kilohertz, but 2 kilohertz all the way up to 15 kilohertz. This carrier frequency is inputted into this voltage waveform as a triangle wave, and we use whatever frequency reference we want. So if this is 60 hertz, so how we vary the frequency, this wave that we're trying to make is just going to get squished or wider. So, you know, the more squished it is, the faster we're going to, our motor's going to turn. So, you know, if you're running some high-speed machine, this could be, you know, 400 hertz or more could be possible. Click the head. And maybe you're wanting to run at low speed. As long as your motor's capable of running at this low speed, you could be running with a very, very wide or long stretched out part of your wave. So how this works is this carrier frequency set, so it has a set area that it works in, but depending on what frequency reference we want, we will just choose our intersecting points. From there, that picks how wide of a pulse we need. As our wave starts to build up, Our intersecting points get a little wider, so that's why our pulse gets larger, and so on up until where we saturate, where we're on the whole time, and then we start to come back down. These points of intersection start to get smaller and smaller, and that's how we would make, for this example, an upper part of one of our waveforms. Got a question here. What causes noises in the motor line changing gears? Oh, like changing gears. Oh, okay. So what causes noises in the motors? Carrier frequency. You're going to notice if you run a motor across the line, it's going to be real quiet and nice. And then whenever you run it with a drive, it could be at low carrier frequencies. It could be a little more noisier. That's just the actual vibrations in the laminations that make up a motor that we talked about before. Remember that that stator has those little chunks of iron broken up in between there, and that's those laminations actually kind of vibrating and making that noise. Now, as you increase your carrier frequency, you're going to notice that that noise kind of goes away. Well, it's just because it goes to a higher frequency that you can't hear, or that I can't hear anymore anyways. So that was a good question. So there's carrier frequency. We were talking about our voltage waveform before. If you look at our current waveform, it looks great. So our current waveform, I like to call it a shark tooth pattern. So voltage is instantaneous. So that's why it kind of looks like it's square wave that's alternating. Okay, but current takes time to change. So whenever that IGBT switches on and off, it's going to go off, but it can't shut off instantaneously. So this middle point here, it takes time to shut off. So it comes down, and by the time it's at this point, the drive's already ready to fire the IGBT again. So we fire the IGBT again, and it makes this little sawtooth pattern going down through here. So as you increase your carrier frequency, what do you think is going to happen to this sawtooth pattern? It's probably going to get a lot smaller and smoother, right? So our current waveform going to our motor will be better, as long as we don't have a lot of voltage transients and long lead length issues. You would be fine with running a higher carrier frequency up to a certain extent. You got to remember, if you're switching these IGBTs a lot more often, what happens? Excess heat's going to happen. So these IGBTs are going to heat up quicker. So you may have to deal with a derate, especially if you're loading this up to its full capacity. There's built-in safeties that will protect the drive, but you're definitely firing those IGBTs more, which is going to create more heat. Hey, it makes a nicer waveform, but you got to deal with that. So a lot of your commercial applications like this higher carrier frequency because they don't like to hear the motor upstairs. Also, with our voltage, I'm going to backtrack just a hair. With our voltage waveform, this looks like a square wave, but really this is like the RMS voltage or average voltage of the cycle. And if you would look at it as the average voltage, this would look a lot more sinusoidal than it visually looks like from our oscilloscope reading. So it's still pretty sinusoidal, but you really see that difference with the current waveform. Just a little note there. You obviously want to make sure if you're going to be running a drive with your induction motor, or if you have a PM motor too, that you make sure that the motor's able to handle it. Most motors nowadays are able to handle these drives because they know you're going to be running them on there, but just make sure that it's able to handle this this pulse width modulation that's coming into the motor. Okay, so make sure the actual motor can handle this higher voltage that it could be seeing. Looks like we have another question. Oh, something to mention. Someone was maybe helping me out. Carrier frequency will reduce at low frequency on our drives to prevent overloading the IGBTs. That is very true. I think, yeah, I think you can disable that though too. Yeah, you can adjust that if you'd want to, but that's very true. Okay, let's talk about our different control methods. It's our different control methods that are available with most drives. The names could vary a little bit, but for the most part, they're going to be pretty similar to this. We have our basic control, which is our V by F control, and then we could step up to V by F control with PG. PG is a pulse generator. Pulse generator is basically our encoder, so we're getting feedback from our motor. What's an encoder do? It actually gives us the position of our rotor instead of us having to guess what the position of the rotor actually is or what the rotor is actually doing. So we're getting feedback from the motor. Then we have open loop vector, which is does not use a encoder, and it makes I would like to say a calculated guess on where it should put this vector at to give us the most performance. And then we have closed loop vector, which is our best control method, which uses a encoder in conjunction with this vector control to give us the most torque per amp, the best control, the best speed regulation, speed response, the most amount of speed control range that's possible. Okay, so we can get very low speed control. V by F control is broken up into constant torque or variable torque patterns. Okay, so like our fans or our pumps could be a variable torque pattern. If we reduce some of this voltage through that mid to lower range area, we can save some energy. This is where those affinity laws comes in, and we're able to get some good energy savings with our fans and our pumps if we're able to run it just a little bit lower than our 60 hertz frequency. Okay, so you can see big savings with that. That's a variable torque V by F pattern. So voltage per frequency. With your V by F patterns, you can always run above 60 hertz. They're just showing 0 to 60. You just have to make some adjustments to run above base frequency. And then your control, it comes down to, we can get starting torque, 150% starting torque at around 3 hertz with this. So not that great, but for what you're probably using it for, you're not really trying to run this low speed control, tight control. So very loose, as long as it's in that flowing that close to that amount of CFMs or whatever you're using it on, then you're okay. So pretty loose, really simple. And then you have your constant torque V by F pattern, which is is the straight pattern. So if we follow this one at 30 hertz, you're going to see half of 230 volts right in the middle, smack dab in the middle. And you're going to get that constant torque out of that motor. That method does not require any auto-tuning. It's always recommended, auto-tuning. But not recommended. You can do very high speed, so we can do 400 hertz or probably even more. You can so that's for your high speed machining. If you little known information about the motor, you could use that too. Very simple control. And then we have V by F with PG, a little bit tighter. So your speed regulation. Your speed regulation gets a little bit better, 0.03, because we actually know the position of our rotor. All right. And then we go to the open loop vector. Okay. You're going to want to auto-tune with this to get the best performance. Without an encoder, look how good our speed regulation is. So we're using this vector algorithm, figure out the position where we get the most IQ and ID, which is our torque producing current, and the most magnetizing current. We want it to be right square in the middle here. So this is the perfect situation where we want to be at to get the most torque per amp for our situation. So we're just guessing that rotor's location in this situation. That's why closed loop's definitely going to be a lot better. So our speed control range goes way up with this. Our speed regulation goes way up. We have very tight control. We can get excellent starting torque, 200% rated torque at 0 RPM. So there's that servo-like control that we talked about. Capable with an induction motor. Remember, this is an induction motor. Like I said, a lot of applications may not need that, like a fan or a pump, but there are some systems that need that type of control. So we have that available. 10:21, got a little bit of time. I would like to talk about some special designs. The U1000 or U1000 or our Z1000U is a very cool drive. It's got low harmonics, built-in, fully regenerative. So whenever I say fully regenerative, it's not stuck in any kind of capacitors. This is actually an AC to AC converter, okay? So we're just, there's no switching to DC. It's just AC to whatever our new frequency that we want to output switching. We use very similar to a regular drive's IGBTs, but these IGBTs are bidirectional. And there's actually a couple more. So instead of our 6, around like 9 of these IGBTs that are bidirectional for this U1000. It's all in one package, very low harmonics. Because we don't have that diode front end, we don't have that issue, that clipping issue that creates a lot of harmonics on our input side. I think this is the only drive like it on the market. Then we have our G7, which last generation, but we still sell it. It's a great drive. Instead of having that that basically 2 square waves, this has an extra level, okay? So this extra level that we're seeing is because we're grabbing the DC bus halfway through and using an extra set of IGBTs for each of these phases. So you have twice the number of IGBTs in these drives, but it creates a lot more sinusoidal output, gets rid of common mode issues. It helps you have less issues with bearing currents compared to normal drives. Allows you to run very long motor leads. We can usually go up to 500 horsepower with these. And then finally, not a low voltage scenario. So remember, this drive is a medium voltage drive, okay? So we're talking kilovolt range, but I just wanted you guys to see these steps that are introduced with this this medium voltage setup. So we have 9 levels with this. So that's a very cool design. And then we have our options. So our available options, you can get extra option cards where you can get more I/O, more inputs, more outputs, more analog inputs, or more analog or more digital inputs available through our drives if you need more than what's on the terminal board already. We have tons of network communication options. Some of them are even included in some of our drives. And then encoder feedback, so you can get that really tight control, that servo-like control is available with just a small little option card. And then power options. So maybe you have one of those drives that don't have a DC link choke, or you're wanting an input or output reactor, or maybe you want you have power outages and you want to keep your CPU active on your drive so you don't drop off your comms that we talked about before. You could get some power options like that, and all that's available on our website. But very cool stuff with drives. Just remember, with a drive, you can save a lot of money in a lot of your applications, and you have great control. Even at our lowest control method, you don't have the issue with starting across the line. They've become very cheap, especially the smaller units that rival the cost of a soft start or something like that. So you might as well just get a drive and have that full range available to you. So that's pretty much it. Pretty close to an hour. Remember, if you want to receive CEUs, just send us a short email saying you want the quiz. Take the quiz. If you don't want CEUs and you still want to take the quiz, by all means, just email us or email me, Daniel Schubert at Yaskawa. I think that's on the email on the invite. So feel free to email me. Any questions? What is the meaning of PG? Yeah, PG is just a pulse generator. Okay, that's a kind of the name for an encoder. So we generate pulses. On most encoders that we use, they have an A and B pulse. Okay, depending on how wide that pulse is going to tell the drive how fast that rotor is actually turning, and then depending on the A and B pulse, which one's leading and which one's lagging, that's going to determine which direction the rotor is actually turning. So it gives us direction with an encoder and also the speed of the actual rotor, which is very important for our vector control method or our V by F with PG control method. So can become very useful. You can get very good control out of that. All right, thank you guys for attending.